Good morning, everyone, and thanks for attending this talk at the AMM 2021. My name is Vincent Rubiolo. I'm the cloud architect here at IoT.bzh, and during this talk we'll discuss data continuity from sensors to the cloud. Now, a little bit about us. We're about 30 engineers here in the west part of France, in Brittany, as you can see on the map, and we're passionate about embedded Linux, and especially about deploying AGL into as many devices as possible, in boats, in cars, and we successfully did so in production through our RedTimeSeries product, which provides AGL for long-term supported devices back at the end of 2020. I've put down a few links here. If you're interested, you can check on us and visit us. We'll be very happy to see you on our website. So, as to what we're going to talk about today, you might have seen or will watch both Julien Massot and José Bollet presentations about, for Julien, RTOS, for José, the security model of RedTimeSeries, which is basically an offering from sensors to the cloud going through real-time operating systems. I'm put down this schema here, this diagram. We'll get back to it pretty soon during our presentation. Sufficient to say that there is a real-time operating system part here. José will likely talk about SE Linux and the security model, and for the target of our talk today will be mostly around the cloud part, a bit of security, and also sensor and data. And that's what I try to detail in our agenda here. We'll go over a few things about the typical connected car, be it for connectivity, long-term support, or security. Then we'll move on to the various typical issues that can be seen in these setups. We'll then lay out our proposal and our vision here at IoT for how we can solve these kinds of issues, and then we'll follow up and wrap with a recap and certain perspectives on what we can do here. Alright, so first, the modern vehicle. As most of you are aware, it's become a very complex system. There's a lot of connectivity here, and one of the predominant problems is how do you pull the sensor data out and potentially into the cloud. Hundreds of sensors from dozens of buses. And you also might have heard about the move from specific domain controllers in the car to a few more compute clusters, more functional architecture that we can mention. So that helps. As a recap, before we move on, it's about dumbing down the sensors and putting the smarts in one or several compute clusters, which are more similar to what you can find in data centers. And that move helps with respect to collection of sensor data. However, it's still a very complex system. With respect to cloud connectivity, it goes two ways. The first one is vehicle to the cloud. We have to handle things like latency, bandwidth, link quality issues. Then the other way, which is from the cloud to the vehicle. More and more car makers are actually allowing you to control your car from the cloud, mostly through companion apps, and of course the data flows the reverse way. In both of these models, the connectivity is often random, contrary to a fixed IT or data center perspective. Connection goes up or down. If the car is connected to cell towers, they have to manage handover when that works. When it doesn't, the link just drops. We have to handle that kind of problem here. There is a need to manage the link quality, as I just mentioned, and we also need to prioritize the data queues. And we'll see what this means in a minute. Another very important thing is security, of course. Security first because of the increasing topic, which is over-the-air updates, being able to securely update critical parts of the car over the air. And so we need crypto, we need strong security, we need rollback as well. Nobody wants a connected car basically stranded in an underground parking lot because some ECU failed to upgrade and has now to be towed out. We don't want that. Identity and security is also a major thing here. And two things which need to be noted. One is the static part, which is about defining, mostly during at car manufacture time, which equipment is allowed to access which other equipment. And then there is a contextual part. And we'll see what this means in the coming slides, but it's sufficient to say multiple different personas need to be able to access the car data in a dynamic manner, depending on their profile, and that cannot be codified into the car manufacturing time. So two important things here, the static and the dynamic part of identity. And of course the cloud side infrastructure needs to be secured, it needs to scale, load balanced, the usual problem here, especially as you're connected potentially hundreds, thousands, or even billions of cars. One other very important thing is cyber attacks. I mentioned just security a few seconds ago. Connected cars, because of their complexity, expose a much bigger attack surface to assailants. I put down 3 points here. The in-car computer is very complex. Engine control, it's connected or somehow connected. We'll see what this means with respect to the Cherokee hack in a minute, to an infotainment system. And then more and more car makers are deploying companion apps, meaning you can control features of your car through your smartphone. Fortunately, for the people, we should say, less fortunately for the car makers, there was several high-profile hacks that have raised that awareness towards cybersecurity here. You might remember that how the security researcher hacked the Jeep Cherokee and fully and remotely over cell towers and 4G networks actually stopped the engine as the car was driving in the middle of a freeway. Very impressive. And one notable thing here is that the supposed air gapping between the infotainment and the engine control actually didn't work. It wasn't proof, basically. Tesla has also seen some issues infecting the companion app of the car with malware. The researcher were able to actually remotely unlock the cars. And finally, the Nissan Leaf. Troy Hunt, one of the prominent security researchers, managed to get access to the climate control through the cloud API of the Nissan Leaf cloud infrastructure, which was actually completely unsecure. So high-profile hacks, the focus is definitely on cybersecurity here. And you've noticed more recently in the news how very high-profile attacks, I'm mentioning SolarWinds here, have put the focus into the supply chain. SolarWinds was, as I said, very high-profile, likely carried by a nation-state. We'll see whether that applies to an infrastructure like automotive. But it stressed an important aspect, which is it doesn't need to be the end device that's basically attacked for it to be under siege, so to speak. It can be the infrastructure the other way. And in the SolarWinds case, that was the update mechanism, which was poisoned by malware, thus distributed to entire fleets of network equipment here. So cybersecurity, definitely. And finally, as I mentioned, this talk is basically two parts. The first part is around the concept we're discussing here. The second is about what we think IoT.bzh we can leverage to solve these kind of issues. The last bit of that first part is really the focus on long-term support. I've put down two diagrams here, one on the left here and another on the right. So the one on the left is about smartphones. and one on the right is about automotive. Even though both of them are not the same here, of course, there is a similar trend going on, which is the owners will hold on to their device for a longer period of time than before. And for the automotive industry, it's around 12 years. Now, bear in mind, this is actually longer than the actual lifespan of the car. It means it will actually change owners at around the 12-year mark. And this means that there is a need to maintain the infrastructure around these connected cars for a longer period of time. Here, if we talk about these figures, 12 years, we're talking 10 plus, which is becoming typical. And that will also become a differentiators for OEM themselves to provide something that is well and long supported here. So definitely a differentiator for long-term support. Now let me move on to the second part of our talk, which is here our vision at IoT.bzh on how we can solve some of these problems. And what I'm going to detail to you in the second part of this presentation is basically how we're pulling data from car sensors, replicating them into a local data store, we chose Redis, selectively replicating that Redis store into a cloud backend, which allows us to bridge the edge and the cloud, and then on the cloud side, you're free to choose whatever you want to do with that data, basically. Jump into a public cloud or continue to a private cloud infrastructure, but being in charge and in control of that infrastructure bit here. And finally, we'll see how that allows to do it from a security perspective from end to end, and that being done through the AGL security framework, and we'll see that in a minute through the OpenID Connect integration here to handle identity. All right, so here is the general diagram we're going to follow during our presentation here. You'll see excerpts, smaller excerpts here, but sufficient to understand that on the left here is the edge part, on the right is the cloud part, and we'll see the center brick that allows to bridge the two, cloud publication service, and then the transport part, internet, and the public clouds here. The data flow being from here, through the application framework, through the internet, to the cloud publication binding. Okay, if we start with the left part, the data publication architecture and the edge or the car itself. How are we doing that? So we rely on two different bindings in the AGL way. You're familiar with the notion of binder and binding that is at the core of AGL. We use a signal composer, and so we can pull the data out of the sensors from their different buses, be it from the CAN bus, Modbus, or any bus that the binding support. There's a plugin architecture which allows us to add new buses as they're coming to life. And the signal composer is used, that's what the diagram shows here, to put the sensor data in the Redis database through the Redis binding, which is another binding we're introducing that allows to interface a Redis data store with the AGL runtime model here. The signal composer uses this to insert the sensor data into the store. It's a generic binding, all of the RedisTimeSeries, because we're using the time series extension of Redis, allowing us to store time-stamped data into the store. And we also contributed support for binary data as well. It's currently being reviewed as a pull request with the original project, and we hope it's going to enter mainline soon. So that's for the edge side. Now, as we're moving more towards the cloud side of things, the cloud publication binding, cloud publication service with the bindings on basically both ends. You have to think about the binding as the nexus for data exchange here, the sensor data. It reads from the Redis data store we filled in previously, also makes use of the Redis binding. You can see that here on the diagram. And then it writes into the remote store, which is on the other side, on the cloud side. And one important point which I wanted to focus on is that it uses the binder transport to actually bridge the gap between the two. And how does that work? If you've used some of the more advanced options of the AGL application framework, you know there are two options which are here, WS Server and WS Client, which allows to expose some WebSocket endpoints as a server and use them as a client on the other side. And the way we do that is we actually take the Redis API, the various verbs of the API in the AGL way, and we expose that as a client so that the edge side can mount it, so to speak, and then insert the data into the Redis database. But when it does so, it actually doesn't know where the binding actually lives. We have a binder on the cloud side, we have a binder on the edge side, and both of them communicate transparently from a binding perspective here. That's what I wanted to stress that point. And that also allows us to handle the unreliability of the network, which I just mentioned a few minutes ago. We get notifications on disconnection, so we can act accordingly. If the transport supports it, we can also get bandwidth notification changes. And with the system I mentioned, which is the data queues, in the binding we sort the data according to its priority. When the link goes back again, we can selectively choose what we actually send to the cloud. Namely, the most important thing would get replicated first, and the less important things last, if at all. Or only when the connection, for instance, is of sufficient quality, say you are within a Wi-Fi range. Now, one thing you might ask is, especially if you've used Redis, well, Redis already provides a replication mechanism. Well, why aren't you guys using that? And the reason is, if you use the standard Redis replication, you get no control as to what is replicated. As soon as the link goes up, then the data starts flowing, but without any regard as to what goes first, what goes last. So that's the reason we decided to take this approach. And the other reason, which I will get to in this slide, here we're more on the cloud side of things. The other reason I mentioned is because Redis, we chose it on the edge and also on the cloud because it's very efficient as a store. But on the cloud side, it can easily be substituted for either another data store, say SQL, or more like a transport, like MQTT or CoApp, through the plugin system of the cloud publication binding, basically. And as I hinted at earlier, that block on the cloud side is allowing you to select what you want to do. This is still, at this point, your own infrastructure. You host it wherever you want to be hosted. We can see that in a second. And then you can choose, for instance, to go into Azure, AWS, Google, any public cloud, with, if you choose the MQTT transport, for instance, or another transport that you might find suitable. Or you can continue and host everything in your own data center. Right now, the reference implementation is actually packed into an LXD container, but it's very easy to change the container format and host it on something that is more suited for production and scalable, like Kubernetes, and run your workloads over there. So that's it for the cloud side of things. Now, let me get back during a second to security. We mentioned that the security between the edge and the cloud is very important. It's critical in this case. We've seen the Nielsen hack we've seen before. And it's all the more important that, as I said, the data access can be done by different people, different accreditations. Think of the car that is in service in production. It's been uploading sensor data or other kind of data like maintenance, metadata related to the cloud. And now we have different personas, so to speak, that want to access it, like car maker, the dealership post-sale, or the mechanic for maintenance. And each of them needs to access their data, only the data, and these kind of permissions can change over time here. So we need to be able to finally separate the access and who accesses what here in this case. And the way we are doing this is we're integrating OpenID Connect into another binding, which we call the OIDC, for OpenID Connect, a secure gateway. And what it does is it protects the endpoints, the WebSocket endpoints we saw just earlier. It protects them that they've been exposed by the binder. It protects them, and then it also extends the Synagora permission system through identity that has been gathered from the cloud in this case. Let's get a bit into more detail. Here is the bigger diagram we talked about earlier. And right now we're going to focus a bit more on this part here, the secure gateway, and this part here. So as I said, the secure gateway, it will connect to identity providers in the OpenID Connect way, be they social identity, social logins, or more maybe from a production perspective, an authority you might have deployed yourself. And then it will do the mapping between that identity here and the Synagora static permissions. That mapping will be done, part of it through the identity store here, that is inside the secure gateway. And the combination of these two elements allow to model very complex scenarios. For instance, in the maintenance case, you might have the car mechanic which checks into the virtual booth at the mechanic store, and after doing that, so it triggers the identity provider login. We can add supplementary two-factor authentication in this case by means of a physical fob that say they will tag onto the bench or in the car itself, and then the car maintenance data will be actually accessible. And in the end, that access can be revoked, for instance, while the other accesses will continue to work. That's what the secure gateway does here. Now, as we're moving towards the end of our talk, let me do a little bit of a recap here. We saw how the modern vehicle actually relies on a lot of connectivity, which is often unreliable and choppy, depending on the data link that's providing service to our vehicle. A lot of sensor data is actually produced, and we need to handle that data flow. Cybersecurity is definitely critical. We've seen how that matters both in car as well as in the cloud infrastructure. And also we had a little bit of a look as to how we see that problem being solved with the different tools provided in terms of the application, the AGL application framework, as well as the OpenID Connect integration here. In terms of perspective, if you're interested by playing with that proposal and the first implementation we have using the AGL application framework, here is the URL. The cloud publication binding can be found on GitHub. You have ready-to-use binary builds for major distribution or supported platforms as well. And we definitely welcome contribution and feedback if you have any in this case. I've put down also a few links here to a website and to RedPesc in general that I presented earlier. And as we wrap up for our presentation, if you're also interested in the various security papers that I mentioned here, I've put some links in there. The EU has put an interesting white paper about best practices for securing cars, which I think can be of interest to anyone working in the industry. And with that being said, that concludes my talk at this point. If you have any questions or any feedback, please let me know, and I'll be very glad to answer them. Thank you.